Muy bien, vamos a continuar con las...
Okay, we'll move on with the next presentation, which will be given to us by Mr. Jose Maria Azorin. He comes from the Miguel Hernandez University. He'll be talking to us about interfaces. The floor is yours. Thank you for your introduction. As the moderator has already said, my name is Jose Maria Azorin. I'm a researcher at the Miguel Hernandez University in Elche, and I'm going to show you an eye tracking interface which can be applied to any type of device, and specifically, it is useful for people with a high degree of disability. Now, the outline of my talk will be the following. First of all, I'll give you a general introduction, and I will be putting forth different systems that are based on this eye tracking methodology. Then I'll tell you about the architecture of our system and what are the characteristics that have to do with its hardware and software. Later, we will be focusing on the basis of the whole system, which is this eye tracking algorithm, the algorithm that allows us to determine what direction the person is looking to in order to issue a command that is sent to a device. And then we'll show you some of the results, experimental results that have been obtained when working on a robot, and then I'll try to draw some conclusions. As I've already mentioned, the goal of this work is to write an interface that allows us to control any type of device, but on the basis of eye tracking technologies. This is what the name that it receives in English, and most of all, it is geared towards people with a reduced degree of mobility. What are the applications? There are very diverse. For instance, managing a computer with a mouse, or sometimes even word processing systems through a robot or a automatic system. What is an eye tracking system? Well, the name says it all. It's a system that allows you to track the eye, the ocular movement, and see exactly where the eye is looking to, in order to translate that into a command, an order. And there are two different technologies that can be used, either through a camera that captures images from the ocular area, and later on you can try to detect the direction the eye is looking at, and then we can use an electroculography. Basically, we use signals that through electrodes located around the eye, and that allows us to track the direction of the sight. If we capture images through a camera, there is two further types of tracking, what we call head-mounted systems or table-mounted systems. What are the head-mounted systems? Well, again, self-explanatory. Basically, we just locate on our head a camera that tracks the person's eye. If the head moves, there will be no problem because the camera is focusing on the eye. And as you can see here, there's a fitting. Basically, the camera is mounted on the person's head and doesn't move. But we have table-mounted systems, and the difference between them, as you can see, is that the person can move his or her head freely. There's no camera mounted on top of them. Whereas in this case, the measuring device, the camera, is located on a table. And as you can see, it's just fixed on some type of surface. So it is. The device does not measure the eye, the ocular movement, but rather the angle of the sight. Basically, you can see the movement, and that's what the device receives. What is the solution that we bring forth in this type of work? We can see that the head-mounted system is very intrusive, and it is not very comfortable for users because they have to carry it around. The table-mounted systems on their side uses infrared light on the human eye in order to establish this side angle, and it is necessary to establish the direction which that person is looking to. So we try to do away with all of these obstacles. We want a non-intrusive device without infrared lights, and hopefully the user will be able to move their head freely. We just want to send that signal to a device when the person is moving his or her eyes, not the head. As you can see in this image, this would be the architecture of our system. It includes a camera that captures images of the face of the person. And then in order to translate or detect where that person is looking to, we need to add a couple of devices. First, we need a lighting system that somehow covers the whole area steadily in terms of light. And then, of course, the signal captured by the camera has to be sent towards a computer through some kind of card, acquisition card, and basically we process this within the computer. So on the basis of that image of the person's face, the computer has to infer where that person is looking to. And the computer will determine exactly what type of signal to send to the device. Now, let us break this system down and tell you exactly how it works. Now, regarding the hardware, as you can see, there's a camera and a lighting system with the right type of optics covering the scope of action we're interested in, and then a system that sends information to the computer. From the software point of view, we have used an image processing library, what we call Matrix, and it is very useful because we can process images through different channels. So basically, on the basis of this library, the system captures the person's face ongoingly and then determines the direction of the eye. So much for the architecture. This is the core of the system, the algorithm of the eye tracking algorithm. The goal we pursued in this project is to capture the whole face. So basically, any type of movement that the person does should not have an impact on the results. If the person is moving his or her head, that should not be a signal, only when their eyes move. What are the problems that are involved when trying to recognize this eye pattern? First type of problem, the user might be moving his head or her head. Secondly, every person has different features. We don't have the same shape in terms of eyes or eyelids. The general shape of the face is different. And of course, the lighting is going to have an impact on the process, like in any other system. In order to solve all of these problems, we have considered the following. The user is moving his head. That's not a problem as long as we use a progressive camera. Through this type of cameras, we'll always have a very clear picture of the person's face. We can also develop a customized algorithm for every type of user. And of course, we can work on the basis of several parameters, and then the algorithm can be adapted and tailored to the person's face. And finally, in order to avoid that possible noise because of the lightning source, that source has to be stable. Now, the eye tracking algorithm is made up of the following stages. First, the user. We capture the user's image through a camera, but there's a pre-processing stage. And on the basis of that stage, we intend to locate the center of the eye. We compare that through a reference, and we determine the side or exactly the direction the eye is taking. Let us analyze this. This is based on blob analysis. What do we mean by blob? It's a region of pixels that is interconnected and has some kind of meaning. In this case, the meaning would be a blob representing the eye or accounting for an eyelid, another one for a nostril. So basically, through analyzing these blobs, we take apart the features of the person's face, and from then on, we can also determine the location of the blob, the gravity center or core point for that blob, and by having all of these features together, we can locate the eye and see exactly the direction it's taken. As I have said before, we have to pre-process these data. What do we do exactly? There are three operations. First, we establish the necessary thresholds. So basically, we don't need a colored image. We don't need a grayscale image. We just need a black and white image, very simple. Therefore, the first thing we do is to establish these thresholds and come up with a black and white picture. Then we need to establish the type of features that are needed for the algorithm to process. And thirdly, out of the whole image, we don't want to analyze all of the pixels, but only select the ones that we are interested in. During the threshold establishment stage, well, this is very important because if we process it right, we can separate the eyelids and the eyes perfectly well. Whereas if we fail to establish the necessary thresholds, they will be blurred together, as you can see, for instance, on the right side of the picture. They are mixed. That's why it all depends on the type of user. We have already said that we need to analyze the features, the specific features of every blob. Once we have the thresholds right, we need to know exactly for every blob what is the scope, the area, the gravity center, and the whole box. And we need to determine the area and know exactly what type of blobs we want, for instance, the ones related to the eye only. What are the areas, the significant areas? Well, the ones that are needed specifically for the algorithm, and thanks to the symmetric nature of our face, in theory, we would need just half of the face, but we don't need the whole left or the whole right side of the face. As we can see here, we have the area 1, only the eyes and the eyelids, or the nose area on top of area 1. Why do we add the nose or the eyelid on top of the eyes? Because we want to cross-reference in these areas and see whether the eye is moved vis-a-vis the other areas. We don't want to capture every head movement. We want to select the eye only, and that means that we need to cross-reference this with some other areas on the face. We have already mentioned that we don't want to have this absolute detection, this thorough detection of the eye, because sometimes the head is moving and that might interfere in our signal. So what are the type of references that we have selected? Possible items, the ones prominent on the person's anatomy and not artificial references. We don't want to add any type of sticker or any type of additional element. That's why we have analyzed the role that eyelids, nostrils, or eyes can play. And we have also seen